In circular motion, in the last class we did see how when objects move in circular path, the centripetal force, which is a net force, is supposed to help it to be in its circular path. All right, and we saw some of the other consequences when you have a centripetal force coming into action on an object taking a circular path, because the center of gravity of the object is not the place where the force is acted on. There is a chance of a flip. So flipping action is a possibility, and therefore we need to make some compensations for it and not use only the frictional force to provide the centripetal force. Instead, just tilt the entire road. So in the case of a banked road, that's what we did, right? So we tilt the entire road through a certain angle, and when you do that, the normal reaction has two components, and those components will provide the necessary force. So we saw the normal reaction really doing the work. So the suggested speed on a ramp is a speed with which you can go and not use frictional force to take your car in a circular path. If you go a little too fast, then you need extra friction to come in. If you go slower, then the friction will be the other direction. So if on a ramp, if you're going at the required speed, then the normal forces component is what takes it in a circular path. You don't require the friction. The friction is actually damaging to the tires, you know that, right? So the friction is actually going to wear the tires faster. So if you're taking a turn at the recommended speed, then there is no wear and tear on the tires, and you use the component of the normal reaction to make that turn happen. If you go faster or slower, then friction comes in and then the tires wear off. So if it says 30 miles per hour speed limit on a ramp, you go at that speed and then your tires will last longer. If you go faster than that speed, then you're actually you can feel that the car is almost like skidding off, right? Mm-hmm. So imagine the force on the tires holding it. The tires will actually get kind of deformed or ripped out. So it scrapes the tire more, and that causes more wear and tear on the tires. So we saw that part of it. We saw why bicycles will have to turn, tilt. Okay, even train tracks, railway tracks are tilted. Yeah, they are. Yeah, wherever there's a turn, you'll see the outer track is a little above the inner track. Yeah, that's a mistake that we did, long back. I'm talking about many years back, when in my first school we had to design a train track railroad system. So on a ping pong table, we used the entire ping pong table and put papers and all this stuff and put sand over it, and basically we made a big tunnels and stuff like that, railway gates which open and close, signal lights that come on and green and red, not the orange, just green and red, just to indicate. So as soon as the trains approach a certain signal, you can see the signal going to green, and the railway gate closes. It was beautifully done. A lot of wiring under the sand. A lot of wiring had to be done under the sand, put that away. The railway gates, tunnels, and everything, and the tracks were made like this. Those angles? Have you seen those aluminum angles like this? Yeah. So we bought those angles and cut one edge of the angle like this, so you can bend it. Okay. And then on wooden planks, we put the two angles like that and nailed it up. So the angles were like this, and we powered the train with the electricity to those tracks. So we provide the tracks with electricity. Not too much, 12 volts only. And the toy train, the engine, which normally is battery powered, now is collecting the power from the tracks. So we had two brushes touching the tracks like that, and it picks up the power from there. and then it runs. So we can control the voltage and make the train go faster or slower. But it was a beautiful thing. But one mistake we didn't think about the banking. So we just constructed everything nice, and all those tracks were laid nicely. And then the first run, the train took off. The first run, it was beautifully running, and at the turn, all of them toppled over. All of them toppled over. The engine, and followed by that, everything toppled over. And I said, oh gosh, didn't apply the physics there. We just were so busy making the tracks without really thinking of that consequence. But the first run itself told us to now check it out. So then we had to tilt the tracks. So we, removed the, nails a bit, put some packing under the tracks there, made the tracks leveled differently. So we raised the track in such a way that the outer track was slightly higher than the inner track. And then we made it a run. It beautifully took a turn. So the faster you make that turn and the steeper you make the turn, you need to angle it up more and more. Yeah, if it actually stops at that turn, you can feel the tilt. You can see the tilt. But normally, it happens so quickly. You don't actually realize it. Roller coasters. When they take a turn, you can see that it is tilted, right? It is banked. It is banked to the appropriate speed. But again, if they don't bank it to the right speed, your head will be hitting here and there more. So if it is properly banked, some of the new roller coasters, they're done so well that you don't even feel the strain. If you go on badly constructed roller coasters, your head will be shaking from left to right because the head is got inertia. Your body is made to go because you're seated nicely and belted together, but the head is kind of free. So the head wants to keep going in the same straight line, so it has to take the hit from the side rest in order to make it go. Okay, so while it's taking a turn, those things will happen. So if it is well constructed, it will be a very smooth ride, even though it's going really fast and taking the turns. The turn has to be gradual. But most roller coasters, the previous roller coasters, there is a horizontal track, and immediately the turn comes, and then they start angling it up. So you can feel the difference. You're going straight, one big jerk, it just twists you all of a sudden. That is definitely not convenient and comfortable. But if you are planning it up earlier itself, gradual turn, and then you can make it steep, really steep. You won't feel anything at all, even if it's going like this. Depends on how fast you're going. And then so what is the formula that you saw? Tan theta is equal to? V squared over RG, right? That's an equation that is there for all, even if it's a bicycle. What angle should the bicycle tilt? Tan theta is equal to V squared over RG. That's the angle. The steeper the turn you take, the more the angle. The faster you go, the more the angle. And the same equation applies for banking of railroads, banking of planes. They all use the same equation. You need to, that's an important equation. Next one, conical pendulum. Conical pendulum. You know what a pendulum is, right? Yeah. The pendulum is a normal one. This is called a simple pendulum. We'll be seeing that very soon in different chapters. This is a simple pendulum where it actually moves in one plane. Now, a conical pendulum is this. That's a conical pendulum. Like a cone. You can see this describing a cone, right? That's a conical pendulum. So a conical pendulum, like that. So it is supported here, and then instead of swinging back and forth like that, it is moving in circles. So the length of the string that is used is L, but the radius of the turn that it is taking is here. This is the radius. So in this case, let's discuss what happens. Now, as this object is going like this in conical pendulum fashion, what are the forces acting on the keys at that position? Or at any position? What are the forces?
Tension.
Tension which way?
Upward.
What else?
Gravity.
Gravitational force. Don't say gravity.
Sorry. Forgive me.
Gravity is just an entity, as I told you. It's not a thing. It's not a quantity. Just like saying light, heat, or mechanics. The gravity is an entity. So you don't, I mean, you can have gravitational field, gravitational potential, you can have gravitational acceleration, you can have gravitational so many things, right? Gravitational force. So you have to specify what it is. Yes?
Centrifugal force.
Centripetal force is not a force that acts on an object. What is centripetal force?
Force required to keep the object in a round.
Yeah, is that an extra force that is coming in, or what is it? You read what I gave you in the last class. Net force. Centripetal force is a net force. It is not a new force. It's a net force of whatever is existing. You get it? Good. A centripetal force is a net force of whatever is existing. So the two forces that are acting on this object is just this, tension and gravity. There's no other force coming in. There's no other force coming in. But yes, there is a net force. Which way? It has to be towards the center because the object is going in a circular path. The net force of this and this together should be that way. And how do you understand that better? Resolve tension into two components. Resolve tension into two components. If this angle is theta, that angle is theta. If that angle is theta, what is this angle? Theta. So what component of tension is acting in this direction? How much of tension is acting in this direction here?
No, L sine theta.
No, tension is what you're resolving. L is not a force. Tension is a force. T? It's an adjacent side. And the opposite side is this one, which is T. Do you understand that part? We are splitting tension into two components. The component that is adjacent to this angle theta is cosine component. And the other component is T sine. Now what do you know about T cosine theta and mg? They are equal because as the keys are moving like this, as the object is moving like this, is this object moving down or up? No, it is staying in that horizontal circle. So as this one is not moving up or down, this force and this force must be the same. So T cosine theta is mg. That leaves us with only one more force left, right? Which is?
T sine theta.
And that is the net force.
Centripetal force.
That is a centripetal force. So the net force is equal to T sine theta. That's the only force. See again, there are three parts. There are three parts of this, all the forces. There's a T cosine theta, there's an mg, and there's a T sine theta. Since these two are equal to each other, there's only one force existing here, and that is T sine theta. So T sine theta is the net force, which provides the centripetal force. Therefore, T sine theta is equal to mv square over r. If I divide these two equations, what do you have? Is equal to? Have you seen that equation before? It's the same old equation again and again. So you can see even in a conical pendulum, finally you end up with the same thing. Tan theta is v squared over rg. So if I spin it faster, you can see the angle increases, right? The angle is going to increase as I spin it faster. Now, you can derive this equation in a different format too, because it's something that's spinning round and round with a certain frequency and time period. You can bring in the frequencies and time periods. How do you do that? T sine theta is equal to mr omega squared, and T cosine theta is equal to mg. Now divide it. And what do you have now? Tan theta is equal to r omega squared over g. So we have r omega squared over g doing the same thing as v squared over rg. It's the same thing. Those two are exactly the same. So if you are talking in terms of the angular velocity and all that, then that will be an equation that will help you to understand it. So what will happen if you make it spin faster and faster? If you make it spin faster and faster, you can see that the angle increases, right? Now, the radius has a maximum value, which is what? How much maximum radius it can take? L. Because here it is spinning with a smaller radius like this. And if the radius increases, what's the maximum radius that it can have is L. Then it is like this, right? When it is slow, it is a conical pendulum. See, that's a conical pendulum actually, because weight is acting downward. But if I make it go faster and faster, it will nearly stretch out like that. Nearly, not exactly. So if I spin it with very high speeds, then only I can get what? 90 degrees. So getting a 90 degree is practically not possible. Why? Because if tan 90, what is tan 90? Tan 90 is infinite. Tan 90 is infinite. Tan 90 is infinite.
You're right.
Tan 90 will be infinite. So if you want this side to be infinite, then your speed should be infinitely fast. The speed of this should be infinitely fast to make it perfectly horizontal. You understand? Why cannot it be perfectly? Because the weight is acting down, so it has to sag. If there is no weight at all, like in outer space, yeah, you can have absolutely flat things. So on zero gravity, if I'm going to spin it like that, it is going to be absolutely, you can't have a conical pendulum like that. It's not going to be like this. So the moment I spin it, it has to be flat, because there's only one force. So in zero gravity doesn't make a difference whether I do like this or like that. It doesn't make a difference. It's just going to be always a full. Again, tan theta should be infinite if you want the angle to become 90. So velocity must be infinite. The same way here. The maximum radius it can take is L. G is a fixed thing. Therefore, you must spin it with an infinite frequency. You need to get it absolutely horizontal. Yeah.
So it's just the acceleration divided by gravity?
Yeah. Hmm? The acceleration divided by gravity. That's a good line of thought. This is the acceleration, and that's the gravity. So if the centripetal acceleration is exactly the same as gravity, then the angle will be. If the centripetal acceleration is exactly the same as gravity, exactly equal to 9.8. So if this is 9.8, and that's also 9. So what should be the angle? What angle gives you tan of that? 45. Tan 45 is 1. Because when you have 45 degree, the opposite and the adjacent sides are equal to each other. So slope is 1. Means what? Rise over run is 1. Okay? Rise and run will be the same thing. Alright, so that's a conical pendulum where you see the same equation coming in. So again, don't memorize any of those equations. You have to think fresh into the problem and then do it. Sometimes you may be given the radius, sometimes you'll be given this length and this angle. You know, the way the questions are designed could be entirely different. But memorizing only this equation and jumping straight into that equation is not the way to go. What you should do, learn these equations, you know, learn what is actually taking place and set these up. Okay? I can show you a problem right now.
Once you get exactly.
Don't see a problem here. Anyway. All right. Here's the problem. A 50 centimeter long string is used to spin an object in circles like that. And the object is spinning making an angle of 30 degrees. The object is spinning making an angle of 30 degrees with a vertical. So if I give you this length and if I give you this is 30 degrees, if I ask you what is the frequency, what should be the frequency of the turn? Like how many spins can it do every second? So what do you have to do now? What you have to do to start off working with this problem is the same as before. What is the force downward? mg. Tension this way. T cosine theta is acting this way. And this one is T sine theta. Okay? And since frequency is a question, we are always now looking into the omega part of it. So T sine theta provides a centripetal force for it to go round and round. So it becomes mr omega square. And T cosine theta is what balances the weight. T cosine theta is what balances the weight. And omega is 2 pi f. So once you get omega, you should be able to get everything. Yes.
Can you explain T sine theta is equal to
because that's a centripetal force towards the center.
Okay. So is that
Say it again.
just the equation for acceleration?
This is this is the centripetal force formula. Since T sine theta is the net force, it's equal to mr omega squared. Now, do you know r? Do you know the radius?
No.
Yeah. Well, you can find it.
You can find it. Very good. So this is 50 centimeters I gave you. And you can find this radius by trigonometry. This is 30 degrees, that's 50. So what should be this? 25. So you can find out that this radius is 25 centimeters. How? Sine of 30. Sine of 30 is opposite over hypotenuse. So sine of 30 is opposite over hypotenuse. So therefore r is equal to 25 centimeters, which means 0.25 meters. So we have the radius. So let's start putting it down. So T sine theta is equal to m r, yeah, we have that. Okay. If you divide both these equations, we have tan theta. Tan theta is equal to r omega squared over g. You have everything there. You have angle 30. So tan of 30 is equal to r, which is 0.25 times omega squared over 9.8. That will tell you how much is omega. And once you get omega, frequency is omega divided by 2 pi. Can you do that? Find out omega first. Tan 30. Omega is 4.75?
I think so.
Frequency 7.47. Yeah, omega is 4.75.
Omega is 4.75. What's the unit?
Hertz.
Radians per second.
Omega's unit, radians per second. Okay. Okay. So omega is this, and so what's frequency? Frequency is 4.75 divided by 2 pi. How much is it?
0.757.
0.75 or 0.76 hertz.
How did you get 4.75? I didn't use that.
Tan 30 times 9.8 divided by 0.25. Take square root.
It rounds up to 0.76.
Oh, you have to put it in degrees.
It rounds up to 0.76.
Yeah, 0.76 hertz.
No, 4.756 or 76.
Oh, this is 4.75.
It doesn't matter.
Yeah, anyway, this is also
If you use the
0.76.
calculator, just not
Yeah.
around.
I'll use calculators.
Yeah, you can use your previous answer itself and then work on. So yes, 0.76 hertz. So typically, I give you a problem for exactly this. It's 50 centimeters. 50 centimeters, and if it is making a radius, if the angle is 30 degrees, which is almost this, it is making 0.76 turns per second. Do you get it? So this actually is making 0.76 turns per second. So pretty much what we calculated is exactly what we got here. Yes,
So you don't need to know the
mass.
you don't need to know the velocity to calculate that either, because like will the velocity always be the same for the radius? Like the velocity and radius are like proportional, or
It's connected, but not proportional now. Because the angle changes. If the radius changes, then the angle automatically changes. So it's not proportional.
would you say the radius and the angle are proportional?
Not exactly true that way also, because
They're connected.
they're connected, yes, but it's not exactly proportional. It is definitely growing. the radius has a limit, it can only go up to this length. The speed is the other factor. So, yeah, how we tackle the problem is exactly this. Now, if you want to know how fast it is moving, how fast is this moving to make that angle of 30 degrees? What's the speed? What's the linear speed? What do you do?
V is equal to
RW?
omega.
R omega. So V is equal to R omega. You can use that to find out the linear speed. What is that? R is 0.25 and omega is 4.76.
5.6.
How much is that?
Oh no, I squared it. I squared it.
Right?
Yes.
1.19 meters per second. That's how fast it is actually moving. The keys were actually moving at a speed of 1.19 meters every second. So make sure that you understand the connections between all these quantities when you're doing this. We'll work some more problems before we move to gravitation. I'm reading out the problem and then just try and picturize the whole thing. A coin is placed 11 centimeters from the axis of a rotating turntable. You know what a turntable is?
Yeah.
So there's a turntable. There's a turntable. Okay? Turntable, the previous record players and all that? That's a turntable. A coin is placed 11 centimeters from the axis of a rotating turntable with various speeds. So this thing can spin at different speeds, and the coin is placed 11 centimeters from the axis. The coin is placed there. When the speed of the turntable is slowly increased, the coin remains fixed on the turntable until a rate of 36 RPM is reached, and the coin slides off. Can you practically imagine this situation?
Yes.
You have the turntable, there's a coin sitting there, and you start turning it on and make it go faster and faster and faster. The coin is still there, it's still there, it's still there, but at a certain speed, the coin cannot hold there anymore, and it slips off. Okay? So what is making this coin go in a circular path? What is making the coin go around in a circle? What is keeping it there?
Friction.
Friction. Which way? How much is friction? How much is that force? Centripetal force. How much?
Mu S times NR.
Mu S times NR. That's right. It is mu S times NR.
Wait, so why is friction towards the middle?
Always towards the middle.
That's the centripetal force.
Yeah.
If something is spinning around and around and then it is able to complete that circle.
So the net force, what'd you say, is the net force then friction by default?
Only friction. Because the forces acting are this. Mg is downward, normal reaction is this way, and this is the only friction that comes in. Normal reaction and weight are balanced anyway. So the friction is mu S times NR. Do you understand that part so far? And that is the centripetal force required. And the centripetal force formula is what in terms of omega? mr omega squared. That's your centripetal force. And what it is saying is this. Okay, what is normal reaction?
Mg.
Mg is a normal reaction, so M goes off right there. So we don't have to know what's the coin's mass. We don't want that. And it also says that at 36 RPM, it slips off. So from there, can you get omega? 36 RPM,
Change it to
change it up, yes. 36 revolutions per minute, change it to how many radians per second?
Change it to seconds.
So 36 revolutions per minute. You need to change it to 36. Each revolution is 2 pi radians. Then divide by 60 seconds. So how many radians per second is that? You understand why I multiply by 2 pi? Because each revolution is 2 pi radians.
3.760.
3.7 radians per second. That's omega. So we have omega. And what is the question asking you to find out? What is the coefficient of static friction? So all you have is to find out this. What is mu s? R omega square over G.
What's radius?
R is 11 centimeters converted to meters. Omega is 3.77 squared divided by 9.8. And that will give you the coefficient of static friction between. Universal law of gravitation. What a universal law of gravitation states? Of course, it is from Newton's law of gravitation. So what is this Newton's law of gravitation? Every mass attracts every other mass. Write it down. Every mass attracts every other mass. Every mass attracts every other mass with a force. Every mass attracts every other mass with a force that is proportional to the product of the masses. That is proportional to the product of the masses and inversely proportional to the square of the distance between them. And inversely proportional to the square of the distance between them. I repeat, the universal law of gravitation states this: every mass attracts every other mass with a force that is proportional to the product of the masses and is inversely proportional to the square of the distance between them.
You say square.
Yeah, d squared. Inversely proportional to the square of the distance between them. Putting this equation together is proportional to m1 m2 over d squared. Now the proportionality sign is changed to an equality sign by introducing a constant, capital G. And this capital G is called universal gravitational constant. Now there is a big difference between capital G and small g. What is small g used for? Acceleration due to gravity, right? Capital G is called the universal gravitational constant. And the universal gravitational constant, why is it called universal? Because it's the same thing anywhere in the universe. Everywhere in the universe, any two masses will behave this way. So the constant of proportionality is fixed, fixed number for anywhere in the universe. And it is 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square.
Meters squared.
Per kilogram square.
Does that like constant the units on that just so it can cancel it out and equal just newtons?
Yeah, it's actually coming from here. You'll see it soon.
Can you cancel?
Yeah.
G is the universal gravitational constant.
See, if you pull G out of that equation, if you make G the subject of that equation, you can see what is G. G is equal to F D squared over M1 M2, right? What's the unit of force? Newtons. What's the unit of distance squared? And divided by? That's how the unit is like that. The unit of G is Newton meter square per kilogram square. So I wrote this unit. It comes from that equation. So this 6.67 10 power negative 11 is a number that is the same across the universe, anywhere. So if you want to find out what is the force between you and the earth, if I want to know how much force is acting on me and the earth. So this is me, and this is the earth, and that's me, not to scale. So my mass is 82 kilograms. And the earth's mass, so this is my mass, and the earth's mass is 6 followed by 24 zeros kilograms. So the earth's mass is 6 10 power 24 kilograms. And how far am I from the earth?
4,000.
4,000 miles, right?
How many times 3 points? No, how many?
Yeah, it is 6,400 kilometers. So, can you find the force between me and the earth? What's the force between me and the earth? I gave you my mass 82 kilograms, earth's mass 6 times 10 power 24 kilograms, and I gave you the radius of the earth, which is the distance between me and the earth's center. It's center to center. Can you see that? So between center of me to center of the earth, it is 6,400 kilometers. So apply that equation. F is equal to 6.67 10 power negative 11 times 82, that's my mass, times 6 10 power 24 divided by, what's the distance? This is in kilometers. You can't keep kilometers. So 6,400 kilometers is 6,400,000 meters, which is what? 6.4 times 10 power of 6. But don't forget to square. Yeah, work that out and tell me what answer you get. That will tell you how much force the earth is pulling me with and how much force I'm pulling the earth up. Both the same. The force of attraction between the two masses. I've been saying that so many times. What is the force with which I'm being pulled by the earth?
800.
8. So it should be around there. Yes. No, it's mass. Mass M1, mass M2.
Oh.
This is mass 1, mass 2.
801.18.
Yep. So 801. So that's what I keep saying as 800 newtons, 800 newtons, you know. So the force between me and the earth is 800 newtons. I am pulling the earth up with 800 newtons. Earth is pulling me down with 800 newtons. And this is how we calculate it. Now, knowing this, if I ask you another question about what is the force of attraction between the moon and the earth, then what you have to do is apply the same equation. Apply just the same equation. G, mass of the moon, mass of the earth, divided by the distance between the moon center and the earth center. Yeah.
Could you work that problem out?
Huh? What's that again?
What's the mass of the moon?
Oh, wait, we'll get there.
Oh, you literally just do.
Say 4 times.
How do you do? I don't want to second, comma.
Second.
Think about 7.
I think Graham writes that as times 2.
Yeah, but it's
Are you still struggling with that equation?
Just do
Yes.
parentheses and do times.
What's the problem?
they don't know how to
Take
do
the
the
long shot.
I don't know how to do
So if that is what, if that's the Earth of mass m, and that's an object on Earth of mass small m, and the radius of the Earth is r, what are the forces acting on me? It's a gravitational force, right? What's a gravitational force? Mg, right? What we normally write as mg is the gravitational force, which according to Newton's law of gravitation is, what's the formula?
M1
G m m over,
d r squared.
see that? This is a force between me and the Earth. What we normally denote as weight, mg, is in fact this. Simplifying this equation, we have gm is equal to gr squared. It's a very, very important equation. Yes.
So do you take the bigger mass every time for that, or do you just pick one?
No, because this, the force that's acting on me is mg.
Oh, okay, yeah.
That's why I use that. So, what does this mean? Shh. This is a relationship between capital G and small g. The connection between small g and capital G is this. Now, this is an equation that you can apply to any planet, any star. What is capital G? 6.67 10 to the minus 11. What is this M standing for? Mass of the planet.
Big mass.
What is the small g standing for? Acceleration due to gravity on that planet. And what is R standing for? Radius of that planet. You see it? So if I want to know what is the acceleration due to gravity on the moon's surface, I need the radius of the moon, I need the mass of the moon, that's it. I should be able to get the G on the moon. Right? So that's an important equation that connects this with different planets. So the mass of a planet changes, then gravity of course is going to change. Imagine there is another planet just like Earth, same radius, but the mass is just double. What will be the gravity on that planet? 19.6. It will just double. You get it? So this equation tells you that connection. How is the gravity connected to the mass of the planet and to the radius of the planet? Another question. Last question. Gravity on the Earth is 9.8. If there is a planet, the mass of that planet is twice the mass of the Earth, and the radius of that planet is half of that of the Earth. Can you tell me how much is G there? What I'm saying is the mass is twice as that of the Earth, and the radius is half of that of the Earth. What will be the G on that planet? Huh? How much?
1.4.
No. Okay.
G would be a lot bigger.
This will be a lot bigger, yes. How much?
It would be the same.
Mass is double. So what will happen is for the new graph, this is going to be twice. So there will be an extra number 2 on the top.
8 times bigger.
8 times bigger. That's right. Because radius is half. What is radius is half? Radius is half. Square it. What do you have there?
Why is it 2 on top?
Yeah, it makes sense.
Because the mass is double.
Why is it 4 times bigger?
You are good.
Yeah, that's why you did it right.
Yeah.
If you want to look at it more clearly, this is what you do. This is the gravity on the planet. And then you simplify this. 2me rp square is, you see it now?
Yes.
And then you can see very clearly this 8 times.
That'd be a swell.
Who would lead our campaign?
Make the news some way.